Welcome back. Today we will look at a slightly more complicated situation. Okay. Steady state radial diffusion in spherical particles, but we will add a reaction there. Okay. And this situation finds very many different applications, as you can yourself see when we go through the actual situation. In fact, one of the applications is being presented as a problem here for us to consider. So, steady state radial diffusion in spherical pellets with reaction. So, to do that, to understand this, let us consider doing this problem. Let us consider an enzyme reaction for which the enzyme is immobilized on a porous spherical pellet. The pores could have a high surface area, that is, say approximately 250 meters squared per gram is very standard in these situations. Huge surface area. 1 gram of the substance has 250 meters squared. The pellet itself is placed in a fluid environment. Since the enzyme is immobilized inside the pores of the pellet, the transfer of substance to the site of the immobilized enzyme through the pores and the transport of product out of the pores are expected to play a major role in determining process kinetics. Okay. So, the substrate needs to get to the place of the enzyme, which is in the pores, it needs to get there, and then there the reaction happens, it gets converted to a product, it needs to get out, the product needs to get out of the pores back to the surface and so on and so forth. So, both those are expected to play a role here. Thus, the transport inside the pores needs to be considered rather than the transport to and fro from the surface of the pellet. We are interested in the transport inside the pores. We are not so much worried about how the transport, this is in a fluid environment and the substrate is in the fluid, and how it transfers from the bulk of the fluid to the surface is not much of our interest. The other process, how it goes from the surface through the pores to the site of the enzyme, that is more our interest here. What it has to do is derive an expression for something called an effectiveness factor, which gives a measure of how much the reaction is hindered due to immobilization. Okay. Suppose you had the enzyme free in a fluid, how quickly it reacts. That there is a certain process kinetics associated with it, there is a process speed associated with it. By immobilizing that onto and the pores in a certain pellet here, how much does it get hindered? By how much does the process rate decrease? Is a very important thing to know while working with immobilized enzymes. Okay. So, this is a direct application, very many different applications. Immobilized enzymes are used in so many different processes, bioprocesses across the world to produce products worth billions of dollars a year and so on and so forth. And therefore, this is all depend on whatever we are going to look at in this particular analysis. In fact, people needed to analyze this and then understand this and then design the various aspects of their bioreactors to optimize their production. Okay, let us start looking at this. Spherical geometry, therefore, we will use spherical coordinates. In this case, we are interested in the processes that happen inside the sphere into which the enzyme is immobilized itself. We are not worried about what happens outside. The system, therefore, is a spherical pellet, and let us do a material balance on the substrate. The concentration of the substrate is S over this system. You know what to do now. We go to, it is a spherical coordinate system, go to table 2.3.2-1 to do the material balance. Pick out equation C2 because the concentration, total concentration and the diffusivity are constants, and that is the reason why we are picking C2 over C1. And if you do that, we have already seen this equation earlier. Let me not go through term by term again. So, this is the equation C2, which is the material balance equation, and we are doing the material balance on the substrate here. Okay. So, the Ci is nothing but S, as we know. No, Ci, the concentration of the substrate in the liquid is S, is some S. Let us see how we are going to do that. Whether we are going to use Ci or S, we will see. I think we switch to S. We'll see. So, if you look at the terms that are relevant here, it is a steady state analysis. That is what we have decided to do. Most processes are at steady state for most of the time, okay, except for batch processes. The steady state analysis can be used to make sense of many different situations. Therefore, this goes to 0. There is no variation with respect to time. There is no bulk fluid motion. There is no convective fluid motion, that is, and therefore, Vr, V theta, V phi are 0. This of course remains. There is angular symmetry, and therefore, there is no variation with theta. Theta is this angle. There is no variation with phi, which is this angle, and of course, there is a reaction that is happening here. Okay. So, the only difference between the earlier case, the growth factor, and this case is this reaction term. Okay. For the enzyme catalyzed reaction, the Michaelis-Menten equation is a very good first approximation. We all know this from the various courses that we have done. And also R is the only variable, therefore, we can replace the partial derivatives with the total derivatives. So, if we do that, we get, I am going to replace dI with d effective for the pores and so on and so forth, 1 by r squared d dr, r squared ds dr. Yeah, I have converted, I am going to use S instead of Ci here, ds dr, because the concentration as S of the substrate is what we have decided to use, and therefore, ds dr equals, this is the Michaelis-Menten equation, V max S by Km plus S is the Michaelis-Menten equation. Of course, I am using V max dash and Km dash in the place of V max and K max. That is only because when we immobilize things, the parameter, when we immobilize enzymes, the parameters could change, or they normally change, and therefore, the V max in solution may not be equal to the V max when it is immobilized, and therefore, to differentiate that, I am using this dash here. D effective is effective diffusivity, and if I expand this, it is not equal to 0. So, I cannot take this to be constant and so on. Therefore, I will have to expand this. If I do that, I get minus d effective d squared S dr squared plus 2 by r ds dr. Okay, I am differentiating with respect to r, and I have a r squared here, and so on and so forth. You go term by term, and you get this equals V max dash S by Km plus S. Okay, if you can look at this as r squared ds dr, you do the differentiation term by term using the product rule, and then there is a 1 by r squared term. So, some of those terms will cancel, and finally, you will get this. So, please work things out, pause the video here, work things out if you are not clear. Okay. Each one of these mathematical steps that are shown, I have tried to make them as detailed as possible, but you will have to draw a line somewhere. If you feel uncomfortable, then stop and work step by step. I am sure if you do that, you will feel a lot more comfortable. You do not have to take things at face value. You know exactly how things come about, and that that improves the confidence significantly. It is no longer some black box kind of a thing. Let us call this equation 2.4.3.1 dash 1. For writing the boundary conditions, let us consider the following. We have radial symmetry, okay, and when we model something, that has to reflect some key aspects of reality, otherwise there is no point, right. We have radial symmetry, and therefore, whether you approach using this radius, this radius, this radius, this radius, you should reach the same condition at the center. Okay. So, that is physical reality, it is a single pellet. How you traverse, and because there is spherical symmetry, the concentration of something at the center has to be the same irrespective of the direction of traversing. So, the substrate concentration at the center must be the same value irrespective of the radial direction followed to approach it. This is physical, this is mandated by physical reality. So, in other words, there cannot be a discontinuity. If you approach here it is some s, and if you approach here it is some s dash, that cannot be the case. Therefore, there cannot be a discontinuity in the substrate concentration at the center, irrespective of the radial direction of approach. And the only way in which this can happen is that the concentration at the center either goes through a maximum or a minimum of the profile. Okay. In this case, it will be a minimum because there is a continuous decrease. It could be a maximum. Mathematically speaking, the derivative needs to go to 0. It has to be either physically speaking, the concentration needs to be either a maximum or a minimum at that point for reality to be valid. Okay. So, the only way this can happen is that if the derivative of the substrate concentration at the center is 0. Think about this. If you are unclear about this, send me a mail, send me an email. We will discuss more, and I will try to clarify this better. Therefore, at r equals r, the derivative of the substrate concentration with respect to radius has to be 0. This of course is the condition for the maxima, as you all know, or one of the conditions for the maxima or minima, extrema, let us say. This is certainly the condition for the extrema, ds dr equals 0. Equation 2.4.3.1-2, and at r equals the surface, r equals capital R, the concentration of substrate is the substrate concentration that can be measured as 0. And the above equation, which is this, needs to be solved with those boundary conditions to get at the particular solution. If you do that, we will get the variation of the substrate concentration with radius, and that is what we are after. Okay. What we are going to do is, I am going to use this opportunity to introduce to you a slightly different way of solving, which makes the solution a lot more general by the way we get the solution itself. Okay. We are going to use something called non-dimensional parameter. So, whether it is a pellet of this size or a pellet of this size or a pellet of this size, it does not make a difference in the solution that we get. The solution is valid in general for any size just by looking at it. You do not even have to substitute various things and see. Just by looking at it, that becomes valid. And that can be achieved by the use of non-dimensional variables. We will look at non-dimensional variables from a slightly different context later in the course, but let me introduce the non-dimensional variables. As the name implies, non-dimensional variables do not have a dimension. Okay. So, there is a non-dimensional variable for distance, there is a non-dimensional variable for other things, and so on and so forth. Okay. Let us look at this. We are going to, before solving this, we are going to convert the equation in terms of non-dimensional variables and solve it, and thereby the solution becomes general. We just have to finally substitute the actual values of a system to get the particular solution, that is all. And the solution in terms of the non-dimensional variables themselves is applicable in general. It is not dependent on the particular radius and things like that. So, let us define the following non-dimensional variables. Let us call the ratio of the substrate concentration to the substrate concentration at the surface as x, x equals s by s0, 2.4.3.1-4, and y is the ratio of the radius at any point by the radius of the pellet that we are looking at, the immobilized pellet that we are considering here, 2.4.3.1-5. Now, we will have to convert the previous equations in terms of our non-dimensional variables. Okay. This is going to take some work, and so please be with me. So, this is what we are trying to do. We are trying to write the earlier equations in terms of x and y, which are our non-dimensional variables. A lot of math is coming up. So, what is ds dr in terms of our non-dimensional variables? That is one of the things that we have earlier. So, we know by chain rule that ds dr is ds dx, dx dy, dy dr, right. So, this is the standard, this you recall from your earliest math course, engineering mathematics course. Ds dx is nothing but S0 here, from here x equals s by s naught, and therefore, ds dx is S0. Let us keep dx dy here, and dy dr from this is nothing but 1 by r, and therefore, ds dr becomes s naught by r dx dy. D squared s dr squared also we need, that is nothing but d dr of ds dr. ds dr we already have here, but let us do this like this. Let us call, because we need it in terms of y and so on and so forth, right. Therefore, d dr ds dr, which can be written as d dy ds dr dy dr. Okay, we are just following the chain rule, function of a function. Therefore, d dy of ds dr dy dr, and that equals d dy of ds dr is nothing but s naught by r dx dy as given here, and dy dr is 1 by r. Okay. And therefore, we get d squared s dr squared as s naught by r squared d squared dy squared of x. Therefore, the differential equation that we had earlier in terms of ds dr d squared s dr squared becomes minus d effective s naught r squared d squared x dy squared. If you want to look at the differential equation, let me show that to you. We have this d squared s dr squared, ds dr, and of course, these are okay, these can be directly substituted. So, this is what we are converting to non-dimensional variables, and so we have minus d effective s naught r squared d squared x dy squared plus 2 by y r s naught by r dx dy equals V max dash, instead of s we have s naught x km dash plus s naught x. Okay. Stop the video if you are not comfortable with this, go back, substitute the various things, convince yourself that this is indeed the case, okay. Then restart the video. Okay, hopefully you would have convinced yourself. Now, if we divide throughout by s naught d effective r squared, we have d squared x dy squared plus 2 by y dx dy equals minus V max dash x r squared divided by d effective km dash plus s naught x. Okay. And this mere division to take d effective s naught by r squared we are dividing by, and therefore, we get this. Okay. We have taken the negative to the other side to make both these terms positive here, both these were negative here, both those are positive. So, we have this. Now, we have it of a form that you are comfortable with, or you are already familiar with from your mathematics courses. Before we proceed further, remember we are looking at the effectiveness factor. Therefore, let us do something here. We are going to group the right hand side term as something like this. The left hand side remains the same, d squared x dy squared plus 2 by y dx dy, that remains the same, equals, let us call this V max d effective km, let us take the r squared out, and so what remains in the numerator is x, and since we have taken the km outside here, we will have to include a km dash here, km dash, and therefore, this becomes x by 1 plus s naught by km dash times x. Let us call this equation 2.4.3.1 dash 7. Now, let us define a couple of non-dimensional parameters, and we will talk about the utility of them much more later. We will talk about it a little bit now also at the end of this. Let us define something called a Thiele modulus, which is designated as capital M T, as a reaction rate divided by a diffusion rate. Okay. Remember, this is an immobilized situation. In the free situation, of course, the rates are going to be much higher, because the immobilized situation is limited by the transport of both the reactant and the product, reactant to the site of the reaction and product away from the site of the reaction. And therefore, we would like to compare the pure reaction rate with a pure diffusion rate. A reaction rate, a representative reaction rate is this: R cubed V max dash by Km S naught, some sort of a first order you can say. And a diffusion rate is nothing but in terms of a diffusion coefficient, R d effective S naught. Therefore, this is called a Thiele modulus. This is a standard modulus that is used if you look at heterogeneous reactions, and therefore, let us define this Thiele modulus for our situation. Equation 2.4.3.1 dash 8. We will also define a beta as S naught by Km dash. 2.4.3.1 dash 9. This one is defined in such a way to give us this: the reaction rate is first order when S naught is much less than Km dash. You know this. So, you take a look at the Michaelis-Menten equation and recall this situation, and that is being reflected by this beta here, and that is the reason why we have taken S naught by Km as a different parameter here, beta. So, the reaction rate is of first order when S naught is much less than Km, and beta is S naught by Km accounts for the deviation from the first order kinetics. You can view that as providing us with how much it deviates from the first order kinetics. For large values of beta, of course, the reaction is zero order, it does not depend on the concentration at all, and for small values the beta of beta, the reaction is first order because it is going to depend on S naught. Okay. In terms of these non-dimensional variables and parameters, you could write the equation that we had earlier as d squared x dy squared plus 2 by y dx dy equals this. We have manipulated this in terms of the Thiele modulus. To write it in terms of the Thiele modulus, you can of course go and check this. We have written it as R cubed V max dash by Km dash S naught, R d effective S naught, and so on and so forth, to get the Thiele modulus here. And of course, this remains the same, x by 1 plus S naught by Km dash is beta, therefore 1 plus beta x. 2.4.3.1 dash 10. And the boundary conditions are, earlier we saw the boundary conditions that at the surface the concentration is the concentration of the liquid, and at the center the derivative must be 0, right, for continuity. So, at y equals 1, that is the surface, x equals 1, and at y equals 0, dx dy equals 0. Therefore, we have completely converted our differential equation as well as the boundary condition in terms of the non-dimensional variables x and y. Recall what x and y are. If you are unclear, go back and check, and then it will be clear to you. I have just numbered the equations for the boundary conditions. Now, if I substitute this solution or rather the solution of this equation, of this differential equation, would give us the variation of x with y, and we know what x is, we know what y is, and therefore, it will give us the variation of s with r. And I am going to leave it at that, I am not going to take it forward. You can solve it, you can plot x versus y, and then you can use some typical values of the radius of the pellet and so on and so forth, substrate concentration, to see how things vary. Please do that, that will give you an insight. The usual interest as well as the problem need is knowing how much the reaction is hindered due to immobilization. and that is the effectiveness factor. So, the effectiveness factor is a measure that gives us the hindrance, and we are going to define the effectiveness factor as the actual reaction rate, with all these hindrances, what the reaction rate is, divided by the reaction rate in the absence of mass transfer resistance. Suppose there has been no mass transfer resistance, hypothetical situation, there is no mass transfer resistance. What happens, what is the rate at that thing? That would be the maximum. And the actual reaction rate is what actually happens with all the processes, the diffusion, the mass transfer, and so on and so forth included. So, what is the ratio? How much is it getting hindered by because of the immobilization is given by this effectiveness factor. So, let us get an expression for the effectiveness factor. That is what is needed in the problem. Let us do that. So, the actual rate, I am calling it V act, is to find that out. Let us consider this. This is a steady state situation. Okay. Steady state means at a certain point of interest, the variables of interest should not change with time. Okay. Therefore, there should be no mass accumulation at the surface of the pellet. If it accumulates, it is changing with time. If the substrate accumulates or mass accumulates at the surface, the mass at the surface is changing with time. That is not allowed at steady state, and therefore, there should be no mass accumulation at the surface. This in turn means that whatever substrate is entering the surface needs to be consumed in the pellet for the steady state to be valid. If that is not happening, the steady state is no longer valid. Okay. So, if we look at the rate of entry through diffusion as this minus d effective ds dr at r equals r is the diffusion is the diffusion flux that is given by Fick's first law. We multiply it by the surface area of the particle AP to get the diffusion rate from the flux to the rate. And in spherical geometry, if you recall, the positive r direction is from the inside to the outside. Here the substrate is entering from the outside to the inside, okay, just in the negative r direction, and therefore, we include a -1 here to indicate that direction. So, the rate of entry is Fick's first law at r equals r times AP times -1. Yeah, -1 because the outward radial direction is taken as positive, S entry is in the negative r direction. Since by steady state requirement, the rate of entry must equal the rate at which it is being consumed in the pellet, the actual rate must equal the rate of entry as given here. The negative and negative cancel out, d effective S naught by r, dx dy at y equals 1 is what this turns out to be. I have written it in terms of the non-dimensional variables, times AP must equal the actual rate, the rate at which it is getting consumed inside the pellet. On a volumetric basis, because the rates we are more comfortable on a volumetric basis, d effective S naught by r dx dy at y equals 1 into AP, this is on a surface basis, we divided by, sorry, this is on mass per time basis, we divided by the volume here, we get the volume, or moles per time basis, we divided by the volume to get the volume, and that both are, I mean, the AP is the surface area of the sphere, VP is the volume of the sphere. Surface area of the sphere is 4 pi r squared, volume is 4 by 3 pi r cubed, and therefore, your actual rate turns out to be, you have a 3 sitting here, so that goes up, some of these terms cancel out, r squared, r cubed, therefore, an r at the bottom, that there is an r here, therefore, that is r squared, 4 cancels out, S naught remains, d effective remains, the rest remain. Okay. So, 3 d effective S naught r squared dx dy at y equals 1 is the actual rate. 2.4.3.1-13. Okay, we have been at it for a while. This is a slightly involved thing, it does not matter, let us spend some time on this. One of the lectures being a little longer is fine. If you want, you can take a break, you can pause it, come back, take a look. The reaction in the reaction rate in the absence of mass transfer resistance is the reaction rate if the concentration of the substrate is S0. Okay. That is the concentration of the substrate at the surface. If there is no mass transfer resistance, then the entire inside would have a concentration of S0 of the substrate. That is not happening here, and or that is the situation that we are looking at as the situation, a hypothetical situation that arises in the absence of mass transfer resistance. Since there is no hindrance or resistance to mass transport, the substrate concentration in this hypothetical situation would be the same as that at the surface of the pellet, as I just mentioned. So, the reaction rate at in the absence of mass transfer resistance is nothing but V max dash S naught divided by Km dash plus S naught, the Michaelis-Menten rate with the substrate concentration being the surface substrate concentration. And from these two equations, we get the effectiveness factor, which is the actual rate divided by the reaction rate in the absence of the mass transfer resistance. The actual rate is this, the reaction rate in the absence of mass transfer resistance is this, the entire enzyme, the entire pellet being at S0. And if you reduce this or simplify this, we have taken everything down, dx dy at y equals 1 r squared by 3d effective V max dash, and I have taken Km dash common from here, and therefore, you have 1 plus S naught by Km dash, which is beta here. So, we have the effectiveness factor, we needed an expression for the effectiveness factor is dx dy at y equals 1 divided by, this is nothing but your Thiele modulus MT, apart from this 3 here. Therefore, Thiele modulus by 3 times 1 by 1 plus beta. We will call this equation 2.4.3.1 dash 15. I think this is what we are looking for in the problem. Yep. The effectiveness factor in this given situation. Here we had a spherical geometry with reaction happening. I hope you got an idea as to how to apply these material balance expressions to arrive at very useful insights into the system, and thereby use those insights for design and operation later. Let us stop here for this class. When we come back, we will take things forward. See you then.